In 1933, FDR recommended to Congress the National Industrial Recovery Act, which appropriated more than $3 billion for public works in order to create jobs and stimulate recovery of the economy. President Roosevelt signed an executive order for $84 million to construct the Fort Peck Dam in October 1933. Within a week of the president's signing, the U.S. Army Corps of Engineers opened an office in Glasgow, Montana. News of possible work in Montana spread like wildfire. A tidal wave of hungry, desperate men came to the state in search of work when any pay would have been good pay and any work, good work. At 50 cents an hour for a laborer and a full week of work guaranteed, there was no shortage of applicants. The Corps of Engineers began hiring a workforce that eventually numbered more than 10,000 people. Soon the Army Air Corps began preliminary survey work. The aerial surveys indicated favorable conditions for a dam, which were later verified through more detailed survey work and subsurface exploration. Under the rights of eminent domain, the government has always had the authority to take privately owned property for the sake of the common good in return for its fair market value. Most of the farmers and ranchers in the area had homesteaded their land. The same government that had just given them their land was now taking it back again. And worse, fair market value in 1933 amounted to practically no value. Under the double hardship of depression and drought, land values were almost nil. As far as some landowners were concerned, the government was stealing their land. The first order of business was to build a railroad spur from the main line of the Great Northern Railroad 12 miles away at Wyoto. Then there was the matter of building roads that could carry the heavy construction equipment, and the need to construct 154,000-volt transmission lines from a hydroelectric power generating plant 300 miles away at Rainbow Dam on the Missouri River near Great Falls, Montana. Dozens of construction crews assembled, each with its own task and deadlines, anxious to get to work. And then winter arrived. And this was no ordinary winter, even for Montana. Almost as if nature had sided with those ranchers and farmers who wanted to stop the dam's construction, the brutal winter of 33-34 became an instant test of will and endurance. Temperatures plummeted to 60 below zero. Flesh froze on contact with such a vicious cold. Outdoors, even the simplest act of moving became a test of human will against the will of nature. And yet, for 4 unrelenting months of one of the most severe winters on record, the crews laid the 12 miles of track from Wyoto. The extension of the rail line required that a bridge for the spur be built over the Milk River. Fort Peck was a wide-open, empty place before anyone thought of building a dam there. When the Corps of Engineers opened its office in Glasgow, the only people living around Fort Peck were a handful of ranchers and farmers. Now, with dozens of workers arriving daily, there were no hotels, no apartments or boarding houses for them. Before the Corps could build a dam, it had to build a town. The laborers lived in barracks adjacent to the town itself, 30 men to each dormitory. Each bunkhouse had its own mess hall and 2 wash houses. Single women lived in 2 dormitories and 8 in a dining hall built especially for them. The town itself provided 261 temporary homes built in instant neighborhoods, complete with paved roads, sidewalks, streetlights, and landscaping. Its residents were managers and other supervisory personnel for the dam project. The new town materialized suddenly, complete with a 12-store business block, a 40-bed hospital, a school, a recreation hall, and a 1,200-seat movie theater that in its heyday showed Hollywood's latest around the clock. A central building housed the post office, the town offices, and a community hall. In the central area of the town, a large open mall attested to the military influence. In creating a model town, the designers and planners wanted a clean, safe place, free of saloons, brothels, and gambling houses. The town of Fort Peck proper remained insulated from these dark elements, but not the immediate surrounding area. The town of Fort Peck wasn't nearly large enough to house all the workers who came. Montana law gave hiring preference to married men with dependents, and there was no housing for them in the new Fort Peck. As a result, a number of boom towns sprang up nearby with colorful names, period names such as Wheeler, Delano Heights, Square Deal, New Deal, Macomb City, and Park Grove. The Fort Peck Dam project was divided into three major construction phases. One was the embankment or dam. Two, 4 diversion tunnels with their intake and outlet structures. And third, the spillway. The high ground above the river valley was closest at the site selected for the dam. Clearing operations at the dam site itself were extensive. The efforts to remove trees, shrubs, and other growth resulted in the removal of more than 4 million cubic yards of overburden to get to a firm base. This preparatory work had to be completed prior to actual construction of the dam. There were 2 ways to undertake construction of the dam, such as rolled earth fill or hydraulic fill. The decision to proceed with building the embankment by hydraulic fill was made because extensive soil testing in the vicinity of the dam showed the availability of the right materials on the floodplain for hydraulic fill. Even though the area had deposits of glacial till, quantities in the amount needed were insufficient to construct a dam of this size. Also, a relative lack of stability was a factor. The primary material, finally assessed as being best for the purpose of constructing the embankment, was sand, silt, clay, and gravel. Once the embankment was underway, it was filled with slurry, a general term applied to materials moved with water acting as their carrier. Since this hydraulic fill came from the Missouri River, dredges were needed to move this material from the river bottom to the top of the embankment. Dredging to construct the embankment required removal of material underwater from the river valley above and below the site of the dam. The material was pumped through pipelines from the dredges to the dam using water as the carrier, hence the term hydraulic dredging. This mixture of water and suspended solids is called slurry. The dam, or embankment as it is sometimes called, was comprised of a relatively impervious core confined by 2 permeable shells. Control of these mixtures required continual soils analysis of borings taken in the alluvium and samples taken of the deposited materials in the embankment. The discharge pipes from the dredges and pump boats were located in the shell areas, which allowed the coarse or heaviest material to drop out of suspension first, and the fine or lighter material carried to the core area. A large pool of water called the core pool was allowed to form to accomplish this. In the 1930s, dredges such as the type required at Fort Peck were driven by diesel engines. But the circumstances of the Fort Peck construction were unfavorable for their application. The project was intended to move quickly, and the manufacture of adequate diesel engines was estimated to take at least a year. What's more, pricing and supply of diesel fuel was erratic. And because of this, the engineers made an unorthodox choice: drive the dredges with electric motors, using power from a line estimated to be completed in 120 days. An extensive network of power poles dominated the horizon. With electric power available to drive the motors, the dredges could be put into operation. Of the more than 600 vessels built in the shipyards at Fort Peck, the pump boat barges and the dredges were the centerpieces. The fleet consisted of 6 pump boats and 4 dredges. Each pump boat was 70 feet long and weighed 182 tons. Each dredge was capable of 12,000 horsepower to suck up the slurry from the river. The dredges were connected to a series of booster pumps that pushed the hydraulic fill through as much as 5 miles of 28-inch pipe from the river to the embankment. The slurry was then pumped into core pools behind the embankment to a height of 240 feet, 4 times higher than had ever been tried before. While this work progressed above ground, other work started below. Plans called for a series of diversion tunnels to carry stored water from the reservoir side of the dam to the downstream side. Each tunnel was over a mile long and bored through solid shale. Hence, these tunnels became the sole conduits of the Missouri River around the dam. Now, this would be the only way that water could be released from the reservoir formed by the dam, unless the lake became high enough to be discharged from the spillway. This release through the tunnels today can be controlled and varied. The results of this control and variation serve the purposes of both navigation and the generation of hydroelectric power. Each of the 4 tunnels can carry more than twice the normal flow of the Missouri. The tunnels are critical to the function of the dam. Without them, the force of the river would quickly breach the embankment. The basic concept of the Fort Peck Dam had been to construct an embankment nearly 4 miles long. Before any of the dredging work had started, 2 gravel structures called tows had to be built at the downstream and upstream sides of the embankment. Gravel or stone in the quantity needed was not available locally, so it had to be shipped 70 miles from a gravel pit at Cole, Montana, and from a stone quarry at Snake Butte on the Fort Belknap Indian Reservation, 140 miles away. For months on end, the local population listened to the endless chugging of long trains, shuttling between the quarries and the dam site, as they transported the millions of cubic yards of gravel and rock needed to build the embankment. Large so-called derrick rocks were used to cover the upstream face of the dam, and they're still visible today. Construction of the 4 diversion tunnels, intake, outlet, and gate control structures was a Herculean task. The 4 tunnels vary in length from 5,653 to 7,240 feet, with excavation diameters of about 33 feet and a finished diameter of 24 feet 8 inches. 3 of the tunnels were concrete lined. Only tunnel number 1 would be steel lined for future power development. The tunnels were to be driven in a geological formation known as the Bear Paw Shale, which was approximately 1,100 feet thick. This formation is composed of a dark clay-like shale, which at the surface disintegrates to form infertile alkaline gumbo soil and is characterized by beds of bentonite at intervals from a fraction of an inch to several feet thick. The shale tends to disintegrate rapidly when exposed to air and weathers to a fine dust-like mass. In order to obtain the needed geological data, an experimental tunnel was driven into the hillside not far from the axis of the dam for a distance of 200 feet. The data obtained, however, did not reveal the extent of the faulting actually encountered during tunneling. It was eventually discovered in the pilot tunnel that spraying a bituminous solution afforded the best protection for the exposed shale. It was also found that maintaining humidity at 90% would help prevent drying out of the shale. No serious difficulty was encountered due to powder fumes from the explosive used in the tunnels because the amount of powder per cubic yard was low and the moisture in the air apparently absorbed some. A 60-horsepower mucker carried forward on rails dumped material onto a conveyor gantry, which then loaded it onto a car train. With crews consisting of 12 men each, the speed of driving in the pilot tunnels was remarkable, averaging from 15.2 to 16.9 feet of timbered tunnel per 8-hour shift. By use of the pilot tunnel method, the enlargement of the control shafts and excavation of the shaft foundations was carried out without interruption to the driving of the pilot and the main tunnel enlargements. The pilot shafts for the main and emergency control gate structures were sunk after the pilot tunnels had passed the shaft area. Excavation was done entirely by paving breakers, no explosives being used. In a 5-person crew, 3 men operated the paving breakers, with 1 man on the hoist and another to dump the bucket. The shafts were 8 foot by 8 foot, timbered at 5-foot intervals, which had tight sheeting on the inside. Shaft enlargement in both the main and emergency shafts was by the glory hole method, the material being dropped down the shafts into the pilot tunnels from which it was removed upstream. This enlargement continued until the main shafts were within 30 feet of the top of the shaft foundation. The control shaft foundation required a base sufficiently large to avoid excessive loads on the shale foundation and was 146 feet long by 36 feet wide and 60 feet high. After completing the pilot tunnels, enlargement of the main tunnel was undertaken, starting at the head blocks and proceeding upstream. Concreting operations followed the tunnel enlargement as closely as possible. Work on the tunnel intake and outlet portals began in May of 1934. The contractor's plan of excavation at the outlet portal was to remove the material consisting of disintegrated shale and gumbo to the slope as indicated on the contract drawings. A 1-to-1 slope requirement was based on information obtained from the experimental tunnel and core samples taken along the tunnel alignment. Soon after the start of the excavation, the first indication was given that the ground would not stand up to a 1-to-1 slope. A slide occurred on June 21, 1934 in the vicinity of Tunnel Number 3 portal, which, though small, was followed by a second, more extensive slide on July 7, 1934. This slide affected such an area that it was decided to change the slope from a 1-to-1 to a 1-to-3. At the same time, the location of the tunnel outlet portal wall was moved and the entire cross-section of the wall was redesigned. The excavation was carried out by an alternate block scheme. This system required dividing the entire portal wall into alternate blocks, 20 and 40 feet wide. The 20-foot sections were excavated first, supported, and the wall section concreted into place. After the 20-foot wall sections were in place, the 40-foot sections were excavated, and the same general method for the 20-foot sections were followed, thereby forming the tunnel outlet portal wall. This method of excavating the portal wall area was used in constructing the inlet portal structure. 2 plants, one in the upstream portal area and the other in the downstream area, provided the necessary concrete. Construction work on the tunnels, inlet and outlet structures, and gate control structures proceeded around the clock all year long. Concrete operations continued, even in winter. In addition to the diversion tunnels, a structure was also needed to prevent water from percolating through the foundation strata under the embankment. If water did get into the shale at the base of the dam itself would be in serious jeopardy. So workers drove a steel cut-off wall more than 150 feet into the foundation beneath the dam's core. These slabs of sheet steel, 17,000 tons of it, were linked together to form a waterproof barrier almost 2 miles long. While construction continued on the dam and tunnels, work began on the spillway. Located 3 miles east of the right abutment of the dam, the spillway was to have a maximum capacity of 250,000 cubic feet of water per second, which is 5 times the maximum flow ever observed at Fort Benton, the closest point upstream on the Missouri from Fort Peck, where measurements and records were kept. The purpose of the spillway was to keep water from overtopping the dam by controlling excess flow from the reservoir. The spillway has to withstand the tremendous forces of discharging floodwaters. The spillway is the dam's pressure relief valve. The drainage area of the Missouri River and its tributaries above the Fort Peck Dam is larger than the states of Virginia, Maryland, and Delaware combined. The spillway that's to handle such a burden of floodwater is over a mile long, 800 feet wide at the mouth and 125 feet wide at the discharge end. And at the head of the channel, 16 gates, each 40 feet wide and 25 feet high, either hold in or release the water from the overflow of the reservoir. Each of the 16 gates on the Fort Peck spillway is fabricated steel, weighing 80 tons, and is raised and lowered by electric motors. The entire spillway structure has an under drainage that's 18 miles long to control seepage or runoff from the surrounding hills. This massive concrete structure is set in a natural shale saddle. The spillway structure contains 560,000 cubic yards of concrete, greater than many concrete dams. As the dam neared its closure in October 1937, President Roosevelt paid his second visit to Fort Peck. He spent several days touring the various phases of the project and talking to local officials. His presence was a huge morale booster for the people who had suffered years of hardship building the dam. Workers presented FDR with a gold-engraved cane carved from a Montana diamond willow. Fort Peck again had the attention of the nation. The photographer Margaret Burke White, who'd taken the picture of the incomplete Fort Peck spillway that made the cover of the first issue of Life magazine in 1936, was back to document the president's visit. Then, on the morning of September 22, 1938, an inspection team out on its daily rounds of the dam noticed an irregularity. The distance of a pipeline above the core pool had narrowed from 54 inches to 30 inches. The district engineer immediately called a meeting with his supervisory personnel. They met at the end of the dam where the surveyors had taken the measurements. Around them, the afternoon crews were at work. No sooner had they arrived than the railroad tracks across the top of the dam started to heave. The timbers and the pipe trestles started to groan and crack. The slide happened suddenly. The core pool at the center of the dam began to settle, slowly at first, but then with rapidly increasing intensity. Cracks appeared in the upstream face of the dam, and almost simultaneously, the main mass of the upstream shell started moving out into the reservoir like a gate swinging open from the shore. As soon as the dam broke, the core pool water rushed through the gap and into the reservoir area. 180 men were working in the area when the dam gave. Most of them ran eastward with a slide on their heels. For 10 minutes, tracks, trains, boats, and pipeline rode the shifting mass. Not everyone reached safety. The slide took away 34 men. Yet, miraculously, only 8 men lost their lives. The bodies of 6 men were never recovered, and to this day they lie buried at the base of the dam. Over 5 million cubic yards of earth had moved out into the lake. A board of independent consultants, which had been established when the project began in 1933, was called upon to investigate the causes of the slide. For 4 months, the consultants studied the data and concluded that the weathered shale zone in the foundation was weak, and the stress on the foundation had been too much. The bentonite seams were slipping. The Board of Consulting Engineers conceded there was a risk in completing the dam. But all great engineering works include some degree of risk. The board then recommended finishing construction, although the decision was not unanimous. Assessment of any historic undertaking changes over time and depends invariably on the perspective of the interpreter. Some see Fort Peck Dam as a great triumph of Roosevelt's New Deal. Others point to the fact that the project developed directly out of legislation that was passed 6 years prior to Roosevelt's inauguration. The dam is the story of every worker who contributed to each of the many phases of it. The spectacular tragedy of the Great Slide of 1938, as well as everyday accidents of the sort that plague any great construction project, cost a number of workers their lives. But perhaps the least recognized of the people who turned the idea of the dam into reality are those who toiled at the desks and drawing boards, often as far away from the actual site as Kansas City or Omaha. Engineers, draftsmen, and construction supervisors don't create an image in the popular imagination that's easily celebrated in our culture. Yet it's the work of just such people who've contributed to the advancement of technology in our century. Today, dams have become highly controversial. Development and progress are words that, well, in many quarters just have fallen into disrespect. It's always difficult to put the great works of any other epoch into accurate perspective. But Fort Peck Dam in northeastern Montana is, by any measure, just such a great work.